loading. It's application of radioactive isotopes. What? No. So you barely have to use your brain, which I know suits you. Sorry. Hang on. Got this?
Radioactive what?
There, KJ.
Done.
Radiation. It ain't all bad. There's some good uses to it. So yes, most radiation will kill you and it's a bad thing. But sometimes, you know, a bit of gamma radiation and you can become the Hulk or whatever. Some radiation is good. But how? Well, what way could you use it? So, yes, it's bad for your health, but it has some applications. So here's an example, smoke alarm. Now let me explain it first, how the smoke alarm works. Right, so what happens? You've got, let's see, where will we start? Yeah. You've got here some radioactive isotope. In fact, there's the name of it up the top, americurium-241. This radioactive isotope will release alpha particles, I think, or is it beta? That's not actually important. But we'll say it releases alpha particles. What charge does alpha particles have? It's a positive charge because it's 2 protons, but there's no electrons. So if you look here, what's happening? You have here an electric field, because here's the power, and here's a positive, here's a negative. So there's an electric field here. Yes? Now, if these are positive and the radiation comes out and enters the field, which way will the positive ones want to move? Up or down?
Down.
It'll move down. So this will change the current here, or it detects the current from this causes a current and it detects it and there's no alarm. What happens when there's smoke? Alpha radiation is very easy to block, isn't it? Like, how can you block alpha radiation? You can block it with like a piece of paper. In fact, 2 meters of air would block it. No, actually, maybe less than 2 meters of air, like 20 centimeters of air would block it. So when heavy smoke is it's quite heavy compared to air. I mean, the molecules are bigger, and also smoke has a charge as well. The smoke has a negative charge, I think. Smoke has lots of negative ions in it. So in other words, if you have these heavy negative ions here in the electric field, and you have these positive alpha particles entering the field, what happens? Well, these disrupt the motion of the alpha particles. The alpha particles won't as easily hit the detector. In fact, the smoke will block the alpha particles from reaching the negative plate. So what happens to the current? The current turns off, and then the alarm goes on. So the smoke alarms, not all of them, but a lot of the smoke alarms have a very, very small amount of this radioactive material. And you might say, well, how long will this material last? Well, the half-life is 400 years. So it will last longer than you, which is what you want. Yeah. So...
What if somebody, like,
breaks it and then eats it, is it? Alpha particles are not harmful because your skin is enough of a block to block the alpha particles, but it could damage your skin. If you have a cut on your hand from breaking the smoke alarm, it could get into your blood. That's quite bad. And if you swallow alpha particles, that's quite bad as well. So don't eat Americurium-241. Thank you.
So
When people like Marie Curie, you know, who did a lot of work on radiation about 100 years ago, at the time she would have tasted these materials, because remember 100 years ago nobody knew what this stuff was, and as part of science, you know, she would have tasted it to see if it has a taste or if it has a smell. And this is why she died of radiation poisoning. Because like 100 years ago nobody would know this, because remember we said that radiation is odorless, tasteless, it doesn't react, so you've no way of detecting it. Okay, I would like you to write this down as an example. Now if you want to draw the diagram, you could draw like this one here. It's a simple circuit: battery, positive, negative, alarm, and isotope here. Come on, KJ. I've got enough power. I do. Okay. They don't expect you to remember this for the exam, but you could certainly get a diagram like this in the exam, and you have to explain maybe how it works. Okay, got this?
yes.
Fahad?
Yeah.
Okay. Next example of application of radioactive materials would be fluorine-18 has a half-life of 2 hours. So what you can use this material for? What's wrong? Okay.
Finally.
Yeah. So you don't need to draw this. For example, you know, sometimes you get leaks in your water pipes underground and you want to detect where they are. So you can put this radioactive material in the water supply. Now the advantage of this material is that its half-life is only 2 hours. So it means after 24 hours it's practically all gone. So you can you know, have a notice about don't drink the water for a day. But even if you did drink it, in fact, because it's so small, it will very quickly, you know, not become stable. So it's not really that harmful. But the thing is, you would put in the water supply, and then on the ground you would walk around with your Geiger-Müller counter. Remember that? And then when you hear the counter making a loud noise, then you know you've found where the leak is, because the water is entering the soil. So the water in the soil here will be, it will make the soil a little radioactive. But don't worry, it's only for about 24 hours. Because after 24 hours, that's 12 half-lives. And that's going to, remember, earlier question we had was after 7 half-lives, it's down to 1%. So after 12 half-lives, it's, you know, 1,000,000 of a 1,000 of a percent, it's small. So example, you can use fluorine-18 to find leaks. You can write that down. You know, in the exam, the type of question you would get on this topic would be, give 3 examples of the application of radioactive materials, or a useful application. Okay, you got that?
You shouldn't do it.
Huh? No, no, not necessary. Okay. Next example. So next example is in hospitals. They give you Technet D 99M. Again, it has a half-life of 2 hours. you swallow this, you drink this, and look, yeah, you can actually see this sky is radioactive now. This coloured here is the radiation. So where is the most radioactive spots? Well, you can see there's here, there's this. Now, maybe somebody knows, why are these two spots and this spot here darker than the rest of his body, and these two here under the arms?
Heat?
Not heat, no.
They're not like
No?
no.
I'll tell you what. Does your body want to have radioactive material in it? No. So it'll try to clear it out of your body. The places where this happens in your body is, number one, the liver. Your liver is like your body's organ for cleaning your system, removing contaminants from your blood supply. The other part here, this is called your lymph nodes, and when you're sick sometimes these swell. This also is trying to clean your body. And also under the arms there are lymph nodes as well, also something that's trying to clean. So what's happening is the radioactive material is building up in the liver, the lymph nodes and the armpits, because your body is trying to clean it. Now, will your body be successful? No, it cannot clean the radiation. So what's going to happen is this will eventually not become radioactive and it'll eventually leave. But your body is trying to remove the foreign. Huh?
Why is
Now the reason why is because, for example, if you had some problem with your liver, for example, if this was only half coloured, it would mean half the liver is damaged. It's not doing its job, you know. Or for example, here this is like digestion. You know, sometimes maybe people have blocks. So for example, if you would see a little spot here that was dark, it would mean maybe there's a block there. So it's again like with the leak example, lastly, except it's internal. Okay, so did you write down? So this is a medical example. Also, our patient looks like he could lose a little bit of weight as well. I think could be another problem. Okay, continue.
yes.
Yeah.
And the brain looks small.
Okay. Right, next. So Cobalt 60, half-life of 5 years. This is great now. You can use this as an X-ray. So you can basically use the Cobalt 60 to produce an X-ray. Huh? Not this one, no. No.
Making one?
No, we're looking at useful applications, not destructive. So basically, you know that X-rays work because they send an X-ray through the person and the bones block the X-ray, and so you can see if there's any breaks in the bones. Yeah. Cobalt 60, remember, it produces alpha and beta. Now, alpha particles will not pass through paper, but beta particles, what would you need to block beta particles?
2 meters. 2 meters, at least 2 meters of aluminium.
Some aluminium. So what's happening here is you kind of have an X-ray. You could fire beta particles at the truck, and the heavy equipment in the center of the truck blocks more of the beta particles than the exterior wall, because the exterior maybe is like, I don't know, like 1 centimeter of steel. So some of the beta gets through, but then some of the beta can't get through the wall and the gun on the inside of the truck. So you can use something like Cobalt 60 to do a type of X-ray. Now, why might you not do a normal X-ray? Well, normal X-rays, they're almost... normal X-rays work great when you're talking about people, because the flesh, the skin, it's very easy for the X-ray to go through, but the bone is very difficult to go through. Whereas with something like a car, the difference between the inside and the outside is not so different. You know, there's a big difference between my skin and my bones. True? It's easy to break my skin, not easy to break my bones. But the inside and the outside of a truck, they're more similar. The X-ray wouldn't be able to highlight the differences, but something like a beta particle would. Yeah. So you can use Cobalt-60 as a type of X-ray, usually done at checkpoints. Yeah.
That's what they use at airports.
Correct. Some airports use a cobalt, radioactive type of X-ray machine, and some. Actually, I think most do now.
Luggage bound.
Yeah. Because you can pick up more details. Okay, if you got this one? Yeah. Next. So this is boron 10, and it's stable, and neutrons.
Fighting cancer.
Yes. Now I'll explain how this one works.
Know how that?
Well, it's stable. It's not radioactive. I'll explain what happens now.
If it's not radioactive.
I'll explain what happens now. So, for example, if the patient here has a tumour in their brain, for example, so they have a brain tumour, or whatever, lung cancer, whatever, you kind of already know what a cancer tumour is. It's basically like a part of the body where the cells have become badly damaged and they're not growing properly and they're dangerous to your health. So we imagine that this patient, to make it easy, let's say he has a tumour inside him here. So what they do, it's a new treatment, they inject into the patient boron 10. Now boron 10 is stable, it's not radioactive, and they inject it and they put it right in the tumour. Then they fire neutrons right at the spot where the tumour is. So what happens is the boron 10 gets a neutron, and it becomes boron 11 because it has an extra neutron. Or maybe it's 2 neutrons, I don't know. It has an extra neutron, so it becomes boron 11. Boron 11 is radioactive. So now you have a radioactive material inside the tumour. Now remember, radioactive materials is damaging to your skin and your cells, but if it's inside the tumour and it's radioactive, what will happen? Yeah, well, it will kill the tumour, and then when the tumour is destroyed, the radioactive material can't travel outside the tumour, because remember, what can block alpha particles? Just a piece of skin. So the alpha particles that are released from the boron 11 destroy the tumour that's around it, but then it can't travel out any further. So this is an example of using a radioactive material. Now also the half-life is really, really small. It's nearly zero. So as soon as the boron becomes radioactive, boron 11, then it immediately becomes non-radioactive again. Yes? Okay, so boron 10 is an example here for healthcare. Yeah? Okay. Food irradiation. So, as you know, when you're growing fruits and vegetables, there's a possibility that the fruit and vegetables will become contaminated. Some insects, some animals might contaminate the fruit or vegetables. So one way you can clean the fruits and vegetables and the meat and the fish and the food and all this is you give it a nice gentle coat of radiation. So you spray some Cobalt-60 you run this past cobalt 60. The radiation from the cobalt 60 will kill the top layer of the food. So any dangerous organisms, bacteria that live on the food will be killed by the cobalt 60 radiation. This has two advantages. Number one, the cobalt 60 radiation kills what's living on top of the fruit. This is good. You don't want to eat an insect that will grow in your stomach. True? The second reason is, if it did not kill the insect, it will make the insect unable to have more insect children. So it has two advantages for the farmer. Number one, it cleans the farmer's crop, and number two, it prevents the spread of the insects by reducing their ability to reproduce. So again, this is cobalt 60, useful for food irradiation. So what would you basically, you'd have some cobalt 60 and
if it's like radioactive, for example, from the fruit.
Yeah.
Or if we eat it.
Yeah. What are you asking me?
And what if we eat it?
Oh, with the cobalt 60? Well, this is...
No. After it passes in, it's on the fruit, like for example on an apple.
Well, this is the thing. You don't put the cobalt 60 on the fruit. You just run the cobalt... The cobalt 60 just passes over the fruit, so the radiation hits the surface of the fruit. But remember, we can say skin can block alpha particles, so the radiation shouldn't enter the fruit. It should just bounce off of the surface. But anything that's living on the surface, like an insect, will get the dose of the alpha particles, and that's the end of the syntax. It won't do any good then, because this insect will be protected from the outside of the fruit. So this is only useful for the exterior of the food, not for the interior. Of course, some people don't like this as an idea, that you're eating food that has been treated with radiation. But you got to remember, radiation is around us all the time. For example, right now there's some radiation coming out of the smoke alarm. In the atmosphere there's some carbon-14 that we're breathing in all the time. So there's radiation everywhere. So it's about balance.
Even the
mobile phone, no, mobile phone would be pretty low radiation, I think.
But they said don't keep it in you.
No, that's nonsense stuff. So it's about balance. By putting radiation on the fruit, you're exposing people to more radiation. However, that might be balanced out by the large number of people who won't get a food illness. Do you get what I'm saying? It's all about balance. If you say, no, I don't want my food treated with radiation, then you must be willing to accept more people will get a type of food sickness. You can't have both. Okay, so it's all about balance here. Okay, and the last one here, I think, is good old carbon-14. Yeah, so remember I said we breathe in carbon-14. One day we will die. Sorry to tell you this. And when you die, the carbon-14 in your body will start to decay. By measuring how much carbon-14 is left in your body, you can calculate how long the person has been dead for. So here's the animal eats the grass and everything here is full of carbon-14 from the air. When the animal dies, the carbon-14 starts to decay. You know the graph already. By measuring how much carbon-14 is in the animal, we can work out how long they've been dead for. Everything has carbon-14 in it because carbon-14 is in the air. What uses air to live? It's plants. So the carbon-14 is now in the plants. Then the carbon-14 is going to be in the grass. What eats grass? Cows eat grass. So the carbon-14 that was in the plant, that was in the air, is now in the cow. And what eats cows? People. So there's no way about it. Because carbon-14 is in the air and plants get energy from the air, it means everything's going to have carbon-14 in it. You can't eat something that never used the air. You know what I mean? So this means everything that's alive has carbon-14 in it, because everything that's alive has to eat something else, that has to eat a plant, that has to consume the air. So carbon-14 is in everything. If it doesn't have carbon-14, it means it was never alive. Okay, there's no homework for this lesson because it's just about examples, okay? But I would like you to try and remember at least 3 of these for the exam in case they ask you it.